In this lecture, we will learn about another classification technique, which is decision tree. And the decision tree is also one of the most often used classification techniques, but the mechanism is totally different from logistic regression. And what is good about decision tree is you can use this technique even though you have missing values in your data set, even though you have mixed types of variables in your data set, you can still employ this decision tree. Here, the mixed type data set means that in your data set, there are continuous variables and discrete variables at the same time. In that situation, this decision tree works very well without modifying or transforming your data set. So, in fact, there are several tree-based classification techniques, as you can see from this slide. The first one is CART, which is short for classification and regression tree, that was developed by these four people, and C4.5, which is developed by Quellan at this year. And this CART was developed in 1984. And earlier than those, actually there is a original decision tree, which name is chi-squared automatic interaction detection, which was developed in this year, quite long time ago. So actually, in fact, these days people uh, really do not use this KIDE method, but this CART and C4.5, they are very often used method. And actually, there is a trend. Statisticians, they like this one, but computer scientists, they like this one. This is just a trend. And even nowadays, there is another name, the another decision tree technique, which is C5.0, C5.0. And anyways, the Quillan is a computer scientist, and these four people are statisticians. And the classification, tree-based classification technique that we will take a look at is this one, this CART, classification and regression tree. And the reason is that because I like this one, and I like it. I like too. I like the C4.5 too, but actually the mechanism of these two methods are quite pretty much same. But the way of splitting is just there is just a little difference between these two methods, but uh, the intrinsic mechanism of building decision tree is the same between these two methods. So once you understand this method, then you can easily understand this method as well. But we will not talk about C4.5 in this semester, just this thing, the CART. And why this method is called tree-based classification is that because it looks like a tree, but the upside down and downside is up. So actually this one is trained tree. So there is some terminology that we should know before going through this decision tree. And here is a two-class example. This one is a two-class example where the classes are 0 and 1. And it's still the same that we have to same with the logistic regression case and the other classification technique cases, that we should train a classification model from a training set. So once we train a tree from a training set, we're gonna get a structure which look like this thing, tree-like structure. So this part, so I told you that the upside is down and downside is up. So this part is called root node, and this node is a parent node of these two nodes, and this node is a child node of this node. So the nodes in upper side is parent node and downside is child node. Okay, so this one is a like a root of a tree, so it's called root node. And this one is a parent node of these two nodes, and this one is a child node of this node. And the node at the end of this structure, this tree-like structure, they are called these are called leaf node or terminal node. Okay, so that are the terminologies. And again, once we have this trained tree, then because each of the leaf nodes, each of the terminal nodes has its own class label. So this leaf node is class 0, this leaf node is class 0, this one is class 1. So once we have this trained tree, then we can make it, we can use this, we can use this to classify a new object. So for example, if we have a new data set, which x1 value is 0.89 and x2 value is 0.77, then you just forward this new observation to this root node and then follow the rules. Okay, I forgot to explain this. And every split at every, we say that this is a split of this node, and every this split, we have a rule, we have a yes, this is called rule based on the independent variables. So again, for this new observation into the root node, and then check if this rule is true based on this new data set, because x1 is 0.89. Is that x1 is x1 less than 0.47? No, so it goes this way. And there is a yes, if this condition is satisfied, then this is a convention of decision tree, we goes to this direction, and if the answer is no, we goes to this direction. So because the answer is no, we goes to this part, and then we're gonna meet another rule here. Is asking us, this node is asking us whether or not x2 is less than 0.39, and it's true. Is it true? Oh no, it's not true. So we go to this direction, and again, is x2 less than 0.84? Is it yes? Yes, yes. We goes to this direction, and is x1 is less than 0.87? No, it's because it's at 0.89, so we go to this direction. So this new observation falls into this leaf node, and its class label is 0, so we classify this new object as class 0. Okay, so this is the way of predict the class of new observation. And in fact, this cart only takes binary split, so it has two branches. But for your just for your information, this C4.5, it allows multiple splits, but we're gonna take a look at just binary split case. So this is a kind of cart, the tree structure made by cart algorithm. So this is a two-class example and binary split case. Then we have to, I said that we have to train a decision tree from our training set, and to make a tree, growing, there should be 4 elements. And the first one is a set of binary questions of the form, this one is x in A, and the answer should be yes or no. And the convention in cart is if yes, we goes to left, if no, we goes to right. Okay, so we should have a question that the answer should be yes or no. And we should have a goodness of split criterion. I will talk about this later. And we should have a stopping rule. Stopping rule is usually stopping rule for a pruning, and we will talk about this again in the later of this lecture slide. And a rule for assigning every terminal node to a class. And I told you that each of the leaf nodes should have its own class label, and we should have the way of assigning class label to each of the terminal nodes. And this is very simple. And actually, for a leaf node, for example, in the two class cases, class 1 and 0, if there are more, so we assign a class label by majority voting scheme. So if in a leaf node there are more class 1 objects than class 0 objects, this leaf node has class label 1. If there is more class 0 objects than class 1 object, then this leaf node has class label 0. That's the way of assigning every terminal node to a class, assigning a class label. Then the first one is the splitting criteria, how we split a data into two parts, because in CART algorithm, just binary split is allowed. So to split into two parts, to split a data into two parts, we should have a splitting criteria. Then how to use the data to determine the splits. Then this is a kind of the qualitative criterion that select each split of a node so that the data in each of the child nodes are purer. It should be purer than that in the parent node. Once we split the data into two parts, then the purity should be increased by splitting. So for example, this is a bad split. In a node, we have 40 objects, which class is red, and 60 objects, which class is blue. By some independent variable, in fact, some independent variable, if we split like this, so in the left side, 28 red classes and 42 blue class objects, and here is the proportions still preserved. So this is a bad split. But let us take a look at this case. These 40 red class objects, all of them goes to left and all of these blue class objects goes to right, then this is perfectly pure, and this node is also perfectly pure, but this is not pure. So this is a kind of perfect split, and we want to get this kind of result if possible. But anyways, we want to make those child nodes as pure as possible than this parent node. That's the way of splitting. Then now we should be able to measure quantitatively. We should be able to measure this purity, and then there are several purity or impurity measures. So the opposite of impurity is purity. So we're gonna take a look at the impurity measure, which means that once we split a node into two parts, we should get we want to get as how to say, the impurity should be decreased once we split the data into two parts. Okay, and here this slide shows three types of impurity measure: the chi-square statistic, Gini index, and information entropy. And there is another one, misclassification rate. These three and the misclassification rate can be used as a impurity measure, but in this lecture, I'm going to explain about this information entropy. The reason is that because just I like this one. And once you understand this thing, actually Gini index, even though the measure is different, the concept is same. So the explaining about this information entropy is enough to understand the impurity measure. So I'm gonna use this information entropy for the impurity measure and for the splitting criterion. And the information entropy is computed by this formula. So here is the E indicates entropy, it stands for entropy, and is summation of P minus, yes, minus, this is just multiplication of -1, and summation of Pj log Pj. Here the Pj is the proportion of J's class. So you can think of this as a probability or proportion of data. And the information entropy can be easily explained by this example. And I got this example from internet. And let's take a look at the first example here. And there are 1, 2, 3, 4, 5, 6, 7, 8 animals. And in this set of animals, there are, is it deer? Let us say that this is deer. There are 1, 2, 3 deers, 1, 2, 3 deers, and one rhino, and 1, 2, 3 ostriches, and one lion, right? There are different types of animals in this set among 8 animals. So by using the formula of information entropy, we can calculate the entropy of this set. So among 8 animals, 3 deers, among 8 animals, 1 rhino, and among 8 animals, 3 ostriches, and 1 lion. So by computing this, we can get 1.8 entropy, information entropy. But on the other hand, unlike this case, this set of animals, there are 7 animals, 1, 2, 3, 4, 5, 6, 7 animals, and among those, we have 6, what is that, 6 zebras, right, and 1 hippo. So in this case, by the definition of entropy, we can get this number. And we can see that this set has a high diversity, which means low purity. And on the other hand, on the contrast, this set has a low diversity and high purity. So in the case of high purity, in the case of low impurity, we get smaller number than this one. So information entropy is good for good for it's a good measure to impurity for a set of animals, set of numbers, set of classes. So information entropy, we can see that from this example that information entropy is a good measure to get some numbers on impurity. Then now we use that information entropy to measure the impurity in a node in a tree in a node in a tree. So entropy in a node T is computed by this formula. The difference is just different between this formula and the previous formula is that it's just we have here P of J given T, and that is just simply proportion of objects at node T belonging to class J. So proportion of class J objects at node T. Proportion of class J objects at node T. Okay, that is computed by this formula where n sub jt is the number of class J objects in node T. So in a node T, there is a n1 T is class 1 object, n2 T is class 2 object, n3 T is class 3 objects, and so on. So this denominator is total number of observations in node T, and this n sub jt is class J, number of class J objects in node T. So it's just proportion. It's just estimation of the probability that an object becomes class J, right? So we can simply calculate it once we have a data set in node T, we can simply calculate the information entropy of node T by using this formula. then we should be able to define, what is good split. What is the good split? Then good split must decrease the entropy by the split. So split criteria using entropy, the split should decrease the entropy by the split. So to utilize this concept, the best decision variable and the best decision boundary, they are simultaneously determined by minimizing the following quantity. This quantity. Okay, so actually this one is the entropy of node T1 and this one is the entropy of node T2. So this quantity is in fact the weighted average of two entropies. And because the CART algorithm allows only binary split, let us assume that this node S is splitted into two child nodes, node T1 and node T2. Then by the entropy formula, we can compute the entropy of T1 and we can calculate entropy of T2, this one and this one, right? And here P of T1 is this one, is defined by this one. So let us, and this n of S, n of T is the number of total objects in node T. So this one, denominator is the total number of observation in S, and this one is the number of observations. So we actually, the meaning of splitting node into two child node means that we split a data point, the observed data points of node S into two data sets. Actually, the split means that split of data. So this thing is the proportion of T1 and this thing is the proportion of T2, proportion of the data points at T2. The base is the number of, the denominator is the number of observations in node S. Okay, so the proportion of T1 and proportion of T2, they are used as the weight of each of the entropy, each of the corresponding entropy. So this quantity is the weighted average of entropies. Okay. So if by splitting, if the T1 has more observations than T2, the entropy of T1 has more power, contributes more to this quantity. Okay, and vice versa. So here is an example, two-dimensional example. We have two independent variables and one class variable, and all of those two independent variables are continuous, and we have the coordinates, and here's a class label, class 1 and two class case, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 observations are there. And because we have coordinates on two-dimensional independent variables, so in two-dimensional space, this one is x1, this one is x2, we can make dots on this two-dimensional space for all of these 10 observations. And they are indicated by either circle or dot here. And the circle indicates class 1 and dot indicates class 2. So now you understand that this figure. Then the question is, the question that I want to give you is, how many splits are possible for this data set? How many? Actually, we can split into two parts by this line, or this line, or this line, or this line, this line, this line, this line. So there are 7 possible splits. Then which split should be selected? The split should decrease, should minimize this quantity. So we compute this quantity, the weighted average of the entropies for each of the all possible splits. So let us say that we split data into two parts by this one. Then the rule becomes the question, the yes no question becomes this thing. Is x2 less than 5.5? And in this root node, we have 5 class 1 objects and 5 class 0 objects, okay? Class 2 objects. 5 class 1 objects, 5 class 2 objects. So the entropy of root node is 1, okay? And if we split this data, these 10 data points into two parts by this split and assigning these 3 data points that satisfy this condition goes to here. Oh no, actually, yes, the objects satisfying this condition, this condition is this one, right? So these 7 data points goes to this direction, and these 3 data points goes to this direction. Then in this child node, we have 2 class 1 objects and 5 class 2 objects, right? Then we can compute the information entropy of this node, which is computed by this formula, and its entropy is 0.6831. And how about this one? How about this node? This is perfectly pure, right? Because we have 3 class 1 objects only. So if we calculate the information entropy for this node, we're gonna get the value of 0. Then this node has the weight of 7 over 10, and this node has the weight of 3 over 10, right? So by multiplying its weight to its computed entropy, we're gonna get the weighted average of information entropy, which value is 0.6041, which is less than this one, 1, right? So it's kind of a successful split because we decrease the impurity. No, we decrease impurity by this split. So we do this kind of calculation for not only for this split, for this one, and this one, and this one, for all of the possible splits. So for example, let me erase this part. So for example, let's test another split, which is this one. Then the yes no question becomes this one. Is x2 less than 4.5? The 1 2 3 4 5, it is these 5 data points goes to this direction. So there are 4 class 2 objects and 1 class 1 objects, and these 5 objects goes to this direction. So there are 4 class 1 objects and 1 class 2 objects. Then if we compute the entropy for each of the child node, then we're going to get this number. Actually, they are the same because 1 class 1 object, 4 class 2 objects, and 4 class 1 objects, and 1 class 2 objects. So the entropy becomes the same, and the weight is the same because the 5 objects goes to the 5 objects go to this direction, and 5 objects go that direction. Then the weighted average of information entropy becomes 0.7219, and this value is greater than this value. So by comparing these two, we know that this split is better than this one. So we choose this thing. So for all of the possible 7 splits, we compute this quantity, and among those 7 quantities, we pick up the split having the smallest value of weighted information entropy. Okay, isn't it simple? Okay, that's the first step for growing a decision tree. Then we repeat this procedure. We repeat this thing for each of the child node until each of the child node is perfectly pure. So we got this structure from the previous step. Then we cannot split this part because this is perfectly pure, but we still can split this one, right? So we consider this part only. Then how many splits are possible? 1, 2, 3, 4, 5. Okay. For all of the 5 splits, we compute the weighted information entropy. So for example, if we split by this line, then the rule becomes this one. X1 is x1 less than 1.5? If yes, it goes this direction. So there's only one class 1 objects, and these 1, 2, 3, 4, 5, 6 objects which do not satisfy this condition goes to this direction, and we have one class 1 objects and 5 class 5 objects. Then in this case, the weighted information entropy is this one. So the entropy of this one is 0 because there is only one class 1 object, and the entropy of this node is 0.65, and the weighted average of these two information entropy is 0.5571. Okay, and we compute this thing for this split, and this split, and this split, and the best split, which is corresponding to minimum value of this quantity, is in fact this split. Okay, now this one is perfectly pure, so we cannot split this into two parts, but we can still split this node into two parts. That is the next slide. So by the same scheme, by the same scheme, we split this node into two parts by this split. Then the rule becomes, is x2 less than 4.5? If yes, these four objects go to here, and these two objects go to here. This one is perfectly pure, but still this one is impure. So we can split that into two parts, just like this. By this split, we're gonna get this one. That is called fully grown tree. And because in this leaf node there are only class 1 objects, the class label of this leaf node is class 1. And how about this? This is also class 1. This one is class 2, right? Because there are only class 2 objects. And this one is class 1, and this one is class 2. So each of the leaf node has its own class labels. That is fully grown tree. And in fact, what is the training error of this fully grown tree? That is 0, right? And the decision boundary by this fully grown tree becomes this one. Quite perfectly classified. So actually, in fact, this one is this fully grown tree is kind of overfitted tree. So it's actually, this tree has a overfitting problem. Okay, I already talked about the overfitting problem when I was talking about the model assessment. So this is only good for the training set. But if we have a test set, new data set, this model might not. It's highly possible that this model doesn't work well. And actually, in fact, this example is quite small. small example. So it seems that this decision boundary is good. But if we have many observations, many data points, and two classes are quite overlapped with each other, then this fully grown tree has quite complex decision boundaries. Then so now you can sense of this word overfitted to training set, right? So we cannot use this fully grown tree as a classification model. So what we have to do as a next step is that we prune that fully grown tree. Why pruning? The name of the step is pruning because we prune the tree. Prune is pruning, right? In Korean, 가지치기. So we prune the tree to escape from the overfitting problem by removing some leaf nodes that could harm future predictions. Okay, so decision boundary is too complex and it may not work well for new data set. So we make that decision boundary more smooth, not complicated, not complex. So how do we prune that tree? There is some symbols that are used to explaining about the pruning. This T is the final tree with leaf nodes, that is fully grown tree. Actually, by pruning is a kind of iterative step. So we repeat the same thing, just like growing a tree. This T is at the first step of pruning. This T indicates the fully grown tree, but once we prune some branches, then once we cut off some branches, then the tree after cutting some branches is also final tree T. Okay, so T is a final tree with leaf nodes. At the initial stage of the pruning, it is fully grown tree. And T sub T is a subtree which root node is node T. So for example, in this case, this is capital T, is the fully grown tree, final tree. And if we claim this node as a leaf node, which means that we are going to cut off these two branches, then this part is T sub T, okay? The subtree. This part is subtree. This part is subtree, and this is the final tree, okay? So here T subtree is a subtree which root node is the node T. And this symbol is the complexity of node T, even though it was expressed by the term complexity, is simply the number of leaf nodes of T. So as the number of leaf nodes is large, the tree, we say that the tree is more complex. The tree, if a tree has less leaf nodes, then we say that the complexity of tree is low. Okay, so this symbol is just simply indicates the number of leaf nodes of T, and this symbol is similarly the complexity of subtree T, number of leaf nodes of T sub T. So again, in this example, this fully grown tree, this final tree, capital T, has four leaf nodes, 1, 2, 3, 4. That is the complexity of this tree. And this subtree has two leaf nodes. This subtree has two leaf nodes, so its complexity is 2. And then this R of T is misclassification rate of the tree T, misclassification rate by this tree based on the training set when the node T is claimed as leaf node. So again, if this node is claimed as leaf node, then no, not you. Don't have to think about, oh yes, yes, exactly. Yes, I'm sorry. Never mind. Yes, RT is the misclassification rate of the tree T when the node T is claimed as leaf node. So the T is right after cutting off the branches, right after a pruning. So for example, if we declare this one as a leaf node, then R of T is the misclassification rate of this tree. And this R of T sub T sub T is misclassification rate of subtree T sub T self. So it's misclassification rate by this part. But the thing is that I'm going to explain about these things using this simple example, using the example in this slide. But the thing is that, again, the misclassification rate by this part and the denominator for computing this r's of denominator part to compute this one is the total number of observation. I will explain again using this when we take a look at this example. Then again dash again T again T is a final tree, or the fully grown tree, final tree, and subtree, and complexity of number of leaf nodes of node the tree T, and number of leaf nodes of T sub T, and misclassification rate of the upper part, and misclassification rate of the lower part of the tree. Then we prune the tree at the node T where this quantity is minimal. And this quantity is computed by this formula. The number of leaf nodes of the lower part -1 and denominator part is that, and error rate of the upper part minus error rate by the lower part. Okay, lower part of the tree and upper part of the tree. And this one is the number of leaf nodes of the lower part. Then what does this quantity mean? Where we want to make pruning. What does this mean? This alpha t means that we want to pruning out as many leaf nodes as possible, right? If this one is big, this value is small. If this value is small, this value is small, right? And we want to find the node t of minimal alpha t. Okay, so we want to cut off as many leaf nodes as possible with what does this part mean? With less sacrification of error rate as possible, right? This is the upper part and this is lower part, and we take the difference between these two. So once we prune some part, then the error rate will be increased by this amount. Okay, this one is the upper part, error rate of upper part. Once we split out the branches, once we not split, I'm sorry, once we the pruning out the branches, once we perform the pruning, the misclassification rate of the training set, the training misclassification rate will increase. Is that right? Because you can think of this fully grown tree, its error rate is 0, right? Once, for example, if we prune this part, then the remaining parts error rate increases, right? So as we cut off the branches, we're gonna get increased error rate of the final tree T, final tree capital T. So again, this alpha T means that we want to remove as many leaf nodes as possible, but we still keep high accuracy higher accuracy as possible. Okay, this numerator part means that. So from this example, this one is the fully grown tree, and we named each of the node as T from T1 to T9. This one is T1, T2, T3, 4, 5, 6, 7, 8, 9. And then the possible pruning from this example is we can cut off here, we can cut off here, we can cut off here, right? Which means that if we cut off this branch, two branches, then this T2 is declared, this T2 is claimed as leaf node. And if we cut off these two branches, then this T5 is claimed as leaf node. And if we cut off this part, then this T7 is claimed as leaf node. So there are three possible prunings, three possible choices for pruning, and we compute this alpha t for all of those three possible cases. Okay, then let's take a look at the values. So the first one, let's take a look at this one first. If we cut off this part, then RT is the misclassification rate by this part, right? There's no misclassification here, there's no misclassification here, there's no misclassification here, but there's one misclassification at this node. Because there are 4 class 2 objects at this node, this class label is class 2, then naturally the class label of this node becomes class 1. So this object will be misclassified, so the RT becomes, so only one misclassified among 10 data points, the RT becomes 0.1. And how about the misclassified objects by this lower part, T sub T? There's no objects, right? There's no objects there's no objects that are misclassified by this part, so it becomes 0. Okay, and the leaf nodes, the complexity of this lower part is there are 2 leaf nodes here, so it becomes 2, right? So alpha t becomes is what? 0.1 minus 0 over 2 minus 1. That is 0.1, this value. Okay, and let us consider the cutting off these 2 branches. So we're gonna declare the T5 as a leaf node. Then the error rate by this upper part is only this one, right? Still, the R of T is 0.1. The misclassified objects by this lower part is no, there's no misclassified objects by this lower part, so it's still 0. So at the initial stage of printing, all of these values are 0. Okay, and the leaf node of this lower part is 1, 2, 3, so this value becomes 3. Then we can compute alpha t, and for this split, the error rate by this upper part is this one, so 0.2, and error rate by this lower part is 0, so 0. And then number of leaf nodes of this lower part is 1, 2, 3, 4. So this is 4. Based on those values, we can compute alpha t, which is this one. And what is the minimum value? This one. So we cut off these 2 branches at this stage. Then we're gonna get this pruned tree. And we repeat this procedure. So based on this pruned tree, based on this pruned final tree, we still consider the possible prunings, possible choices of pruning. We can cut off here, we can cut off here. So this one could be declared as root node or leaf node, or this one is declared as leaf node. Actually, because of the matter of size of this example, at this step it's almost done, but the thing is that actually we can repeat this procedure many times in real, a complex tree. Repeat the same procedure with this tree. Then for this one declared as leaf node, and this one declared as root node, we can compute these three values procedure, but let us take a look at the numbers. So in the case of cutoff, in the case of cutting off these two branches, the error rate by this upper part is 0.2 because these two observations will be misclassified as class 1. No, class 2, because the class label of this leaf node is class 2 because there are more class 2 data points. So error rate is 0.2. And how many observations are misclassified by this lower part? In fact, there's no misclassified objects in this leaf node, but there's one. This one is now misclassified by this leaf node, right? So when we compute this one, the error rate by this lower part, that subtree, the denominator, I'm sorry, my pronunciation is not is not good. The denominator part is 10, okay? And we have one misclassified observations over the total number of observation. That is the error rate. We compute it this way. We compute it in this way, this R of T sub T, the error rate by this lower part, okay? You pay a little attention on this computation, please. So the denominator is not what 1 1 2 3 4 5 6 7. Denominator is not 7. Denominator is 10. Okay, I'm sorry, is 10. Please pay attention on this. And the number of leaf nodes of this low part is 2, so this value is 2, and by that formula of alpha t, we're going to get this thing. And when splitting these two branches, then because we have only root node and we're going to assign class 1 or class 2 randomly, then another 5 objects will be misclassified, so error rate becomes 0.5, and the misclassified objects by this lower part is only one object here, so the error rate by the lower part is 0.1, and the number of leaf nodes of this lower part is 1, 2, 3, and 3, so this number is 3. We can compute the alpha t. For the case of splitting, for the case of not splitting, for the case of cutting off these two branches, okay? And we repeat this procedure until when? Until we have root node. Until we can no longer do the pruning or the pruning, okay? So then how do we select the tree? Then what did you do? We grow a tree fully and cutting off all the branches until we have the root node. Then we came back to the origin. Then what did you do? We do nothing. But we do something, actually. We did something. So select the best pruned tree by observing error rates from a validation set. So to build a decision tree, in fact, we have to split a data set into not 2 parts, but 3 parts. So we split data into 2 parts, training set and test set, right? But we again split this training set into 2 parts, training set training, validation set, validation, and test set. So we divide it into three parts. The first one is training, second is validation. Actually, usually the validation is the data set for selecting best parameters of the algorithm. And test is just test set. The purpose of test set is same as what I explained in the previous class. And so we should prepare one more data set, and using only this part, we grow a tree, and whenever we prune a tree, we apply this validation set and observe that validation error. So now let's take a look at this graph. This x-axis is the complexity of tree, which means the number of leaf nodes, okay? And the y-axis is error rate. As we grow a tree, the error rate, the training error rate decreases. Isn't it obvious? And once we have the fully grown tree, the training error becomes 0, right? And then we prune tree, which means that we decrease the number of leaf nodes by each of the prunings. Then the training error increases as we decrease the number of leaf nodes, but the validation error, because at this point that was quite at this point with 0 training error, it was quite overfitted decision tree, so it does not work well for a new data set, which is validation data set. But as we make that tree simpler by pruning, the validation error will decrease, and at some point it will increase again, right? If by passing some points at this range, that decision tree is too simple. So by pruning, by decreasing the number of leaf nodes, we observe these two errors, training errors and validation error, and we decide the number of leaf nodes we stop. In fact, we stop the pruning at this point. Once that validation error increase by a step of pruning, we do not go to that pruning. We come back the just previous step, and then we decide the final tree. That's the way of selecting the best pruned tree. Okay, so that is everything about growing tree and prune tree. And okay, let us take a look at this slide, and then we will finish this session, this class. So decision tree has good points and bad points, and what is good about decision tree is that is interpretable. That decision tree is interpretable because once we have a tree, for example, once we have this tree to become a class 2, we know that property of the class 2 objects by following these branches, okay? x2 is less than 5.5, x1 is less than 1.5, and x2 is absolutely less than 4.5, then on observation becomes class 2 objects. Actually, in this example, we use x1 and x2, but for example, let us say that we train a decision tree to detect defectives in a manufacturing process. This x2 could be on temperature and pressure and so on, the operation characteristics. Then by interpreting the grown tree, we can get some knowledge from the tree that what kind of product, what kind of product, what kind of properties of product will make a defective or well-functioning product. We can make a prediction. No, I'm sorry. We can make interpretation. We can make interpretation based on the grown tree. Okay, so tree is a interpretable technique, and it selects important variables. So let us assume that in our data set there are 100 independent variables from x1 to 1, x100, and there is a class variable. And using this training set, using this data set, let us say that we grown this kind of tree, and the selected variable for the first splitting is, let us say, x79, and for splitting this node, the selected variable is x50, and this one is x60. Then among those, and then let us say that even this structure returns quite accurate predictions for the classification. Then among those 100 variables, only x79 and x50 and x60, only these three variables can be used to classify the objects, and the other remaining 97 variables are unnecessary. They are not needed to make a classification model. And then we know that these chosen variables are important to make a good classification, right? So by making decision tree, we know that we can select important variables, and it is robust to noise. The reason that this method is robust to noise is because we use the impurity measure. Impurity measure is computed based on the proportion of data. So even though, for example, there is a positive classes and negative classes, and here is a positive class which is kind of outlier, which is noise. Actually, the distance how far this object is from the other object, that doesn't matter because we just split based on the variable, right? So it's robust to noise and easy to handle missing values. Even though in our data set there is missing values, we can still employ this decision tree, because when we compute that entropy, that is when we compute the pj given t, we just ignore this missing part, right? Missing value. We can just ignore that. Am I right? Yes, yes, we can just ignore. So for example, it's gonna be a complicated explanation. So actually, yeah, we can just ignore the missing values. Even though there are missing values in our data set, we can still make a decision tree. And there is no assumption about data and parameters, okay? Which means that, for example, in linear regression, we assume that the data points, the observation y comes from the normal distribution. The decision tree doesn't make such an assumption, okay? So it's quite good method for classification, and this method is the method that I use whenever I solve a real problem. This is one of the methods that I try to solve real problems. So it is quite good to know about decision tree. But the bad thing about the decision tree is high computational complexity, right? Is that right? I totally agree with this one, because the search space is huge. For this simple two-dimensional example, at the first stage, we have 7 possible splits. But think about 100 independent variables, and each of the variable could have a possible splits are 3, then there are 300 splits that we have to evaluate by the information entropy. So the computational cost is huge. To make a full search, we have to compute lots of things, lots of possible choices. So high computational complexity is the disadvantage of the decision tree. It takes time, but the thing is that we are not that stupid. The, some people already did some researches to make the fastest split and fastest pruning by some stochastic searching. So in commercial software or even R software, you can grow a decision tree with many variables and many observations. You can get a decision tree within some seconds. And actually, these two bad things are the same indicate the same thing. Interaction terms are not considered, linearity not considered, which means that I'm sorry, I want to erase. For example, let us consider a two-dimensional example. This one, x1 and x2, we have positive data points in this way and negative points here. Then to make a decision tree based on this data set, we have to make lots of splits, right? Because the split can be made orthogonal to the axis, we have to make this kind of splits to discriminate these two groups. So it cannot consider the linearity or interaction terms. Even interaction is a kind of curvature, but you cannot think of that because the split is made orthogonally based on each of the axes. Okay, but for the logistic regression, this is quite simple, quite easy problem because the decision boundaries will be formed here, which means that the S-shaped curve will be made like this. Okay, so this kind of example is quite easy problem to a logistical regression, but this is a difficult problem to decision tree. So that is the bad thing about decision tree. Okay, these two things are bad thing. And I'm gonna stop even though there is the R programs and then examples. I will explain about these things in the next session. So I'm gonna stop here. Thank you for your attention. I will see you again.